Welcome to DAR Tutors. Today, we're delving into a fundamental concept in organic chemistry, radical reactions. This topic is crucial for the IB Chemistry higher level curriculum, especially when studying reaction mechanisms. Our primary objective in this session is to understand the structure, formation, and reactivity of radicals. By the end, you will be able to, first, define and identify a radical. Second, you will be able to explain how radicals form through homolytic fission. And third, you'll be able to describe radical substitution reactions using specific examples. Let's begin with the first objective, defining what a radical is. A radical is a chemical species that possesses one or more unpaired electrons. These unpaired electrons make radicals highly reactive. In contrast to most stable molecules like methane or ammonia, where all valence electrons are paired, a radical has an electron that is alone in an orbital. A single unpaired electron is represented by a dot in its chemical formula. For example, a chlorine radical is written as Cl dot, and a methyl radical is written as CH3 dot. Let's look at the Lewis structures to visualize this. A chlorine radical has 7 valence electrons. 3 pairs are bonded, leaving one single unpaired electron. Here you can see the lone pairs and the critical unpaired electron. For a methyl radical, a carbon atom is bonded to 3 hydrogen atoms, and the remaining valence electron on the carbon atom is unpaired. Notice the dot on the central carbon atom. It's the carbon that holds the unpaired electron. It is important to correct a common misconception. While the radicals we've seen are neutral, radicals are not always neutral atoms or molecules. Radicals can also be cations, anions, or even molecules. What defines them is the presence of an unpaired electron, regardless of their overall charge. Now that we know what a radical is, let's explore how these reactive species are formed. We now move to our second objective, understanding how radicals are produced. This process is called homolytic fission. It is one of 2 main ways a covalent bond can break. To understand fission, we first need to understand the notation used to show electron movement. In organic chemistry, we use curly arrows. A full-headed curly arrow, sometimes called a double-barbed arrow, shows the movement of a pair of electrons. A half-headed curly arrow, also known as a fishhook arrow or single-barbed arrow, shows the movement of a single electron. The tail of the arrow shows where the electron or electrons start, and the head shows where they finish. Let's compare the 2 types of bond breaking. In heterolytic fission, the 2 electrons in the bond move to only one of the atoms when the bond breaks. This process produces 2 ions, a carbocation and an anion. For example, in the fission of a carbon-bromine bond, the bromine atom takes both electrons, forming a bromide ion and leaving a carbocation. In homolytic fission, the 2 bonding electrons are split equally between the 2 atoms. Each atom receives 1 electron from the broken bond. This is shown using half-headed curly arrows. The result is the formation of 2 radicals, each with an unpaired electron. To be clear, heterolytic fission produces ions, while homolytic fission produces radicals. Homolytic fission of a covalent bond is typically caused by heat, or, more importantly for us, ultraviolet UV light. The halogens, like chlorine and bromine, are excellent examples. When chlorine gas is exposed to UV light, the Cl-Cl bond is broken homolytically. UV light provides the necessary energy to break the bond. You can see the half-headed arrows showing each chlorine atom taking 1 electron from the shared pair, forming 2 highly reactive chlorine radicals. These newly formed radicals are now ready to react, which leads us to the next part of our discussion: radical substitution reactions. Now that we understand how radicals are formed, we can move on to our third objective, describing radical substitution reactions. These reactions are a type of substitution reaction where radicals are involved as intermediates. Let's look at the reaction between an alkane, specifically methane, and a halogen, chlorine, in the presence of UV light. The overall reaction is that methane reacts with chlorine to produce chloromethane and hydrogen chloride. This seems straightforward, but the mechanism, how the reaction actually proceeds, is complex and occurs in 3 distinct stages. These are the initiation stage, the propagation stage, and the termination stage. The first stage is initiation. As we just saw, This is where the UV light provides enough energy to cause the homolytic fission of the weakest bond present, which is the silyl bond. This forms two chlorine radicals, and these are the radical intermediates that drive the entire reaction. The second stage is propagation. This is a chain reaction because the products of one step are the reactants of the next. It proceeds in two steps. In the first propagation step, a chlorine radical abstracts or removes a hydrogen atom from the methane molecule. This forms a new methyl radical and a molecule of hydrogen chloride. In the second propagation step, the newly formed methyl radical is also highly reactive. It attacks another chlorine molecule, abstracting a chlorine atom to form chloromethane, our main organic product, and critically, it regenerates a new chlorine radical. This new chlorine radical can then go on to abstract another hydrogen from a methane molecule, restarting the chain. This is why it's a chain reaction. The radicals are continuously formed and consumed, keeping the reaction going. So far, we've seen how radicals initiate a chain and how that chain propagates to form products. But a chain reaction cannot continue forever. We need a way for the radicals to be removed. This is where the termination stage comes in. A termination step occurs when two radicals collide and combine to form a stable, non-radical molecule. Because the concentration of radicals in the mixture is very low at any given time, the probability of two radicals colliding is also low. But it does happen. There are three main ways this can occur in our reaction. First, two chlorine radicals can collide and combine to form a molecule of chlorine gas. Second, a chlorine radical can collide with a methyl radical to form the desired product, chloromethane. This is a termination step because it removes both radicals from the reaction. Third, and less commonly, two methyl radicals can collide to form an ethane molecule. This is an important termination step to be aware of, as it explains the presence of side products in the reaction. This mechanism, which combines initiation, propagation, and termination, is what we call the free radical substitution mechanism. You can see how the radicals are essential intermediaries. The entire process relies on the initial formation of a radical to start the chain. Now, let's explore some important consequences and applications of this radical substitution reaction, starting with its limitations. We've focused on methane, which has only one type of hydrogen atom. But what happens with longer alkanes? In the reaction with methane, we can also get polysubstitution, where more than one hydrogen atom is replaced by chlorine. This occurs because the product, chloromethane, can also be attacked by a chlorine radical. For instance, a chlorine radical can abstract a hydrogen from chloromethane to form a new radical, which then reacts with Cl2 to form dichloromethane. This process can repeat to form trichloromethane and tetrachloromethane. The more chlorine you use in the reaction, the greater the amount of these further substituted products. Another complication arises with alkanes that have different types of hydrogen atoms, like propane. Propane has 6 primary hydrogen atoms on the end carbons and 2 secondary hydrogen atoms on the middle carbon. If a chlorine radical abstracts a primary hydrogen, it forms the primary propyl radical. If it abstracts a secondary hydrogen, it forms the secondary isopropyl radical. These lead to 2 different products, 1 chloropropane and 2 chloropropane, which are constitutional isomers. Mathematically, since there are 3 times as many primary hydrogens, you might expect 3 times as much 1 chloropropane. However, in practice, the ratio is close to 1:1:1. This is because the secondary radical is more stable than the primary one. The stability of carbon-centered radicals increases from primary to secondary to tertiary. This stability is explained by inductive effects, where the alkyl groups attached to the radical center donate electron density, which delocalizes and stabilizes the unpaired electron. The more alkyl groups, the more stable the radical. For example, the tertiary T-butyl radical is the most stable because its unpaired electron is stabilized by 3 alkyl groups. Because the secondary radical is more stable and forms more quickly than the primary radical, a greater proportion of 2-chloropropane is formed. So, we've established that radical substitution of alkanes is not ideal for synthesizing a specific product. However, There are some important applications of radical chemistry that are highly selective and useful. A key application is the radical substitution of methylbenzene, also known as toluene. This reaction is selective. While alkanes react readily with radicals, the benzene ring is very stable due to the delocalization of its pi electrons. Therefore, if we use UV light, the radical substitution reaction occurs exclusively in the methyl side chain, not on the benzene ring. Another important application is in the field of dental composites, which are used to fill cavities. Dental composites are a mix of resins and inorganic fillers. The resin is typically a monomer like bis-GMA, which can be polymerized through a radical addition reaction. The process is initiated by exposing the composite to blue light. A photoinitiator molecule like camphorquinone absorbs this light and generates radicals. These radicals then attack the double bonds of the bis-GMA monomer, forming new radicals, which in turn attack other monomers, building a long polymer chain. This polymerization hardens the composite and fixes it into the tooth. This is an example of radical addition polymerization, a different type of radical reaction where radicals add across a double bond to form a polymer. It's a highly controlled and useful application. Finally, radicals play a crucial role in the atmosphere. Chlorofluorocarbons, or CFCs, can break down in the presence of UV light to release chlorine radicals. These radicals then participate in a catalytic cycle that destroys the ozone layer, which protects us from harmful UV radiation. This is a dramatic example of how a seemingly small concentration of radicals can have a massive environmental impact. The decomposition of CFCs by UV light produces a chlorine radical. This radical then reacts with an ozone molecule, forming oxygen gas and a new radical. This new radical then reacts with an oxygen atom, which is also present in the stratosphere, regenerating the original chlorine radical. This means a single chlorine radical can destroy thousands of ozone molecules, creating a chain reaction of destruction. This demonstrates the immense power of radicals to catalyze reactions. Remember, these are highly important real-world implications of the chemistry we've discussed today. Let's summarize what we've learned today. We've introduced the concept of a radical as a species with an unpaired electron, represented by a dot. We learned that radicals are formed by homolytic fission, where a bond breaks evenly, and we contrasted this with heterolytic fission, which forms ions. We then detailed the three stages, initiation, propagation, and termination, of a radical substitution reaction. Finally, we explored some key applications, including selective side chain halogenation, dental composites, and atmospheric ozone depletion. To solidify these concepts, let's work through some IB-style practice questions. The first question is from your notes. Question 55 asks us to draw curly arrows for the abstraction of a hydrogen atom from methane by a bromine radical. The first step is to visualize the bonds. We have a bromine radical and a methane molecule, which has CH bonds. We draw Br dot and a CH bond. We need to show the bond breaking evenly. First, a half-headed arrow goes from the unpaired electron on Br to the CH bond. This shows the formation of a new BRH bond. Second, another half-headed arrow goes from the CH bond to the carbon atom. This shows the CH bond breaking and one electron staying on the carbon, forming the methyl radical. The products are hydrogen bromide and a methyl radical. This is a perfect example of a propagation step. Here's our second practice question. Question 56 asks us to show the three stages of the radical substitution of cyclohexane with chlorine. Let's break it down stage by stage. First, the initiation step. Just like with methane, UV light causes the homolytic fission of the chlorine molecule, producing two chlorine radicals. Second, the propagation stage has two steps. In the first step, a chlorine radical abstracts a hydrogen from cyclohexane to form hydrogen chloride and the cyclohexyl radical. In the second step, this cyclohexyl radical reacts with a chlorine molecule, forming chlorocyclohexane and regenerating a new chlorine radical, which can continue the chain. Finally, the termination stage involves the recombination of any two radicals. The three possible steps are two chlorine radicals combining, a chlorine and a cyclohexyl radical combining, or two cyclohexyl radicals combining. Now for a more analytical question. Question 57 asks us to predict the number of unique carbon-containing products for the chlorination of methane, methylbenzene, and ethane, excluding termination products. For methane, CH4, all 4 hydrogen atoms are equivalent. Therefore, the first product formed is chloromethane, CH3CCl. However, due to polysubstitution, the chlorine radical can attack the chloromethane to form dichloromethane, then trichloromethane, and finally tetrachloromethane. That gives us 4 distinct organic products. For methylbenzene, C6H5CH3, we know radical substitution is selective for the side chain. All 3 hydrogens on the methyl group are equivalent. We can replace 1, 2, or all 3 hydrogens with chlorine, leading to chloromethylbenzene, dichloromethylbenzene, and trichloromethylbenzene. So there are 3 products. For ethane, C2H6, all 6 hydrogen atoms are equivalent. The first product is chloroethane, CH3CH2Cl. Polysubstitution is possible, so we can replace 2 or more hydrogens to get 1001 dichloroethane, 1022 dichloroethane, 111 trichloroethane, and so on. In theory, you can get up to hexachloroethane C2Cl6, so there are 6 products. Our final 2 questions will challenge you to apply your knowledge to new situations. Question 4 asks you to predict the main product of monochlorination for 2 compounds and explain your reasoning. You can pause the video and try this yourself before I reveal the solutions. Let's analyze compound A, butane. It has primary hydrogens on C1 and C4 and secondary hydrogens on C2 and C3. Because the secondary radical is more stable and forms faster, the major product will be the one that results from the substitution of a secondary hydrogen. Therefore, 2-chlorobutane is the main product. Now for compound B, 2,2,4-trimethylpentane. This is a bit more complex. Pause the video again if you need to. Let's break down the hydrogens. There are primary hydrogens on the 3 methyl groups attached to C2 and on the 1 methyl group attached to C4. There are secondary hydrogens on C3 and a single tertiary hydrogen on C4. C2 has no hydrogens. We know that tertiary radicals are the most stable. There is only 1 tertiary hydrogen in this molecule, on carbon 4. Since its abstraction leads to the most stable radical intermediate, this will be the fastest and most preferred reaction pathway. The main product will be 4-chloro-2-4-trimethylpentane. We'll conclude with our final IB-style question. Question 5 asks you to draw and name all possible monobromolcanes formed from the radical bromination of 2-methylpropane. Again, pause the video and try to solve it. First, we draw the structure of 2-methylpropane. It's a central carbon atom bonded to 3 methyl groups. Next, we identify the different types of hydrogens. All 9 hydrogens on the 3 methyl groups are equivalent primary hydrogens. The single hydrogen on the central carbon atom is a tertiary hydrogen. So we have only 2 types of hydrogens. This means there are 2 possible sites for bromination, leading to 2 possible isomers. If we replace one of the primary hydrogens with bromine, we get 1-bromo-2-methylpropane. If we replace the tertiary hydrogen, we get 2-bromo-2-methylpropane. The question also asks which is the major product and why. The abstraction of the tertiary hydrogen on the central carbon will be much faster because it forms a tertiary radical, which is significantly more stable than the primary radical formed by abstracting a primary hydrogen. Therefore, 2-bromo-2-methylpropane will be the major product. And with that, we conclude our lesson on electron-sharing reactions and radicals. You are now equipped to define radicals, explain their formation through homolytic fission, and describe the mechanism and applications of radical substitution reactions. For further expert tuition in IB, A-Level, and IGCSE chemistry, please contact DAR Tutors. Thank you for watching.